Hi, good evening all. So sorry for the delay. There was a technical issue from my end, so that caused this delay. Okay. So anyways, now we are good to go. So first of all, let me welcome you guys to the Unacademy JEE English. This, as you know, is a brand new channel by Unacademy, which is India's largest online learning platform for ITJ. And on this channel, every concept of physics, chemistry, and maths are being taught to you completely in English. So this is the series that I host for class 11 students, and the topic that we are starting today is gravitation. So this is lecture number 1 of gravitation, and today we'll be talking about Kepler's laws and Newton's laws. Right. Before I get started with today's lecture, let me introduce myself for those of you who might not know me yet. So my name is Rohit Dixit, and I studied mechanical engineering from IIT Delhi. And for almost past 8 years, I've been teaching physics for the IIT JEE Mains and advanced examinations. Now, as a student, I myself was All India rank 447 and All India rank 192, the two stages of the ITJ exams that I took. I also qualified the NTC Stage 2 examination and I was in the top 1% in the NSCP. Now, in my offline experience, I've already coached many students to top ranks in the ITJ examinations. Now, I hope to continue doing that here with you guys online. So as I said, before this year, all my teaching had been offline and all my experience had been offline. This year has forced all of us to adapt. So I have moved to the online teaching. So that is what you guys as students can also do to make sure that your studies are going ahead uninterrupted. Okay, so you guys can get yourselves the Unacademy subscription. So this subscription will help you with the benefits like live classes where you get to interact with your educators on a regular basis. Now you also have live polls and leaderboards. Then you have test series and analysis, and then of course you have live doubt clearing sessions. So these benefits will ensure that your studies are going completely uninterrupted and they are uh, making you not only keep preparing uninterrupted but also steer ahead of the competition that you're facing. Now, these features you already know a lot about. So apart from this, there is another great feature that is there. That now Unacademy is also providing you an opportunity to study from the topmost educators all across India from the comfort and safety of your home. So that's a wonderful opportunity again itself. So how to get this Unacademy subscription? Very easy. First, you'll need to install the Unacademy app. This very first step will unlock a lot of free content that is available on the Unacademy app. You can watch a lot of free courses and a lot of special classes which are absolutely free of cost. So and that will give you a flavor of what you can expect from your subscription. Now, once you plan to finally get your subscription, this is what you need to do. So you can go to the plus section of the app, then select your goal as ITJ and click on the get subscription button. Okay. Now, once you do that, you'll be redirected to the payment page and where you will be asked, do you have a code? So there you can use this code RD Live. So when you use this code RD Live, you will get a 10% off on all your subscription fees, which are now there are two kinds of subscriptions that you can opt for. There's a plus subscription and then there is an iconic subscription. The plus subscription unlocks all the benefits of Unacademy Plus. You are eligible and you can enroll in any of the courses that are going on the Unacademy app and do your studies, be your own mentor of your own studies. Now, iconic subscription is a slightly different one. So this will help you if in case you don't know what to do, you are feeling confused. So hello, S. Pandey, hi Rajesh, hi Motilal, hello Pandya, how are you guys? Also, when you click on proceed to pay, you will realize that you have a lot of no cost EMI options available to make these payments. So any subscription of 6 months and above can have its payment been broken down into a lot of no cost EMIs, which will ensure that you don't feel the burden of these payments. Okay. Now, let's talk about iconic subscription a bit. So iconic subscription is an absolutely new feature that the Unacademy is providing you. So with this subscription, that will take your IITJ preparation to the next level. You will be allotted personal coaches. You will also be attending IITJ workshops from time to time. You'll be receiving expert guidelines. You will get a study planner, and also you will have test analysis sessions, regular test analysis sessions, which will make sure that you are aware of your competition. All right. So again, this subscription will give you more individual attention. So if you want more individual attention during your preparation of the JEE exam, then you can go for this kind of subscription. Okay. Next, let me also remind you that now you have another chance of winning yourself free subscriptions. So you can take part in the next Unacademy Combat, which is going to be happening live on the 20th of December. You can now enroll for this using the code RD Live and not only test your preparation. Hello, good evening, Amod Kumar. How are you? Not only can you test your preparation, see how you stand with respect to your peers, and if you do well, you stand a chance to win some really cool rewards and prizes, which are some amazing things. And along with those prizes, some top positions are also being given away with given away some Unacademy subscriptions. All right, so here is a chance to win some cool prizes and subscriptions. So make sure you are enrolling in this and doing well and winning really cool prizes. Now, those of you who are following us on the JEE English channel of the YouTube can connect with us on the Telegram app using this link. This link will make sure that you are receiving all the notifications timely so that you don't miss out on any of the lectures and sessions that are happening here on the JEE English channel of the YouTube. All right, so why don't we get started with today's topic? As I said, today we'll be starting a new topic, and the topic that we will be discussing today. Sorry. So I haven't been very well. So you'll have to excuse me for that. Okay. So as I said, again, the topic that we are starting today is gravitation, and today we'll be talking about Kepler's laws and Newton's laws. Okay, so let's get started. So first, let's talk about the gravitational force itself. What is that force? So gravitation is a fundamental force of attraction between two objects having masses. So we guys know that all forces can be categorized into four fundamental forces. All forces that you see in nature are in one form or the other, a manifestation of these fundamental forces. So there are four fundamental forces when we talk about fundamental forces. If you don't know about that, so I'll quickly go over that here, and you can watch the lecture that I've taken on Newton's laws. So there I have talked about the fundamental forces. So fundamental forces or the forces of nature. These are the forces that inherently uh, act due to certain inherent properties of all matter. So what are the fundamental forces? So first you have the gravitational force. Okay. Then you have electromagnetic force. Then you have weak nuclear, and finally you have strong nuclear. Okay, so these are the four fundamental forces that we know of. Now we imagine that these fundamental forces inherently are applied by fundamental particles also. So these are called forces of nature, by the way. These are also called forces of nature. These forces naturally exist. Okay, they exist due to some inherent property of all matter. So again, when you we talk about forces in our experience, you have to apply a force, right? So whenever you let's say have a hand, so I have to externally apply a force. If I don't apply a force, this won't feel any force. However, that's not the case with fundamental forces. In fundamental forces, these forces just automatically start acting. So the moment you keep two masses close to each other, they automatically start applying a force of gravity. Nobody has to do anything to make that force start to act. Okay, so that is why these are called forces of nature. They just inherently exist in particles. Okay, so gravitation is one of those forces. Okay, so hello Mahi, how are you? Hi Sumedh, what is happening? How are you? So again, we can also tell you that I can also tell you that this is the weakest of all the fundamental forces and is exhibited by all matter, by the way. So again, anywhere you go, by definition, matter was something that occupies space and has mass. So if something has mass, then they can exert the force of gravity. So force of gravity is associated with mass. This force is associated with mass. Mass, is a fundamental property of matter, right? So this force is associated with the fundamental force property of matter. So that is why we call this also a fundamental force. Right now, out of all these four forces that we talked about, the force of gravitation, the electromagnetic force, the weak nuclear force, and the strong nuclear force, the force of gravitation turns out is the weakest. Okay, so it's the weakest of the naturally existing forces. Okay, but anyways, the effects of such a weak force are also huge. Imagine it's the gravitational force that makes the Earth, which is such a heavy object, go around the sun. So even when I'm saying it is the weakest of all the forces, turns out it's still a huge, huge force and a very important one. For that matter, had the force of gravity not been there, imagine you wouldn't be standing on Earth. We would all be. There would not have been any atmosphere. It is a very, very essential force, so to say. All right. So again, now the mathematical description of this force, of course, was given by Sir Isaac Newton in his Universal Law of Gravitation. So we'll be talking about that in a bit. So first, we'll talk a little bit about history, how people came and developed the theory about gravitation. So Newton's findings would not have been possible, as I said, without the works of many, many scientists. Kepler's laws were the main inspiration. So let's quickly talk about the history of it. So up to a long time, the geocentric model of the universe was widely accepted. So up to a long time, people thought that Earth is the center of the universe and everything is rotating about Earth. It's revolving around the Earth. So people initially thought that Earth is the center and your sun, here might be your sun, here might be your moon. So everything, sun, the moon, all the stars, everything, all the planets, they are all moving around the Earth in orbits. So they are all moving around Earth in circles. So which is a pretty obvious observation, right? So if you stand in an open place throughout the day, what do you observe? You observe sun coming out from here, moving to the top of the sky, then setting it at one horizon. Same would be the case when you observe moon at night, right? So that was a very obvious kind of a conclusion that people thought that okay, that it's the sun and the moon and everything seems to be revolving around Earth, and Earth is the center of the universe. That is what we believe. Now, it was not until the 16th century when Nicholas Copernicus suggested that no, we have been taking it the wrong way. In fact, the model of the universe or the solar system is heliocentric. So heliocentric means sun at the center. Geocentric means Earth at center. So Earth at center. That model is called geocentric. Heliocentric means sun at center. In Latin, I think sun is called Helios. So it was Nicholas Copernicus who first suggested though that no, we have been taking everything the wrong way. Okay, it's actually the sun which is at the center, and everything is eventually all the planets and Earth are revolving around the sun. So this is the model that was given by Copernicus. Now, Copernicus, of course, had a very hard time with this model. The reason was that back in the 16th century, his suggestions were going against what was written in the Bible. So the Bible suggested that no, Earth is here, then heavens are in the sky, and everything is revolving around the Earth. So Copernicus's suggestions went opposite to that. So it turns out he was imprisoned for life, for his ideas. In fact, so it was a tough time. Imagine, but luckily for us, Copernicus never gave up on his ideas. So he was asked to, shun his ideas, say that, he made a mistake and his ideas are wrong, but he stuck to them. He spent his entire life, imagine, in prison, but he never gave up the ideas that he had had. Now, next, he was followed by Galileo. You guys know that Galileo invented telescope, right? So when Galileo invented telescope, what happened was that Galileo could mark the night sky. So at night, he would look at the sky through his telescope. He would chart the positions of different stars and planets. And he confirmed that, if I look at the daily sky charts, then what Copernicus says is making sense. Yes, the positions are changing as if we are all revolving, all the planets are revolving around the sun. So Copernicus suggested this, and Galileo, you will realize, propagated his ideas further. It was actually Galileo who made the idea more popular and spread it because he could prove it. Now, Copernicus only had this theory in his head, right? He had no proof of this. But Galileo, with the help of his telescope, would actually mark the charts, the positions of all the planets on a daily basis, and hence he was able to prove this. Now, again, I don't know if you know this. Galileo was poisoned for this again. He was also threatened. He was told to again completely abandon his ideas or he'll be prosecuted. So he also said no, he didn't want to, abandon his ideas. So he was in fact poisoned. So imagine it was sacrifices of people like Copernicus and Galileo that has led us to, advancement of this theory. So everything that you are studying has come from thousands or hundreds of years of, researches and hundreds of years of arguments, and has had a lot of sacrifice behind it also. So you guys must appreciate this. Now, next, what happened was that when people realized that Galileo, from just noting the sky charts daily, could prove that yes, it is the planets that are moving around the Earth. So a lot of people were inspired by Galileo. So turns out Galileo had this follower who was Tycho Brahe. So he was a huge fan of Galileo. So he was a very rich man. So what he did was he used to own an island. He was a Danish guy who used to own an island. So where on this island he set up a lot of observatories where he had hired people who would actually look at the night sky through telescopes and chart them daily. So for years he gathered this data of night sky. But however, Tycho Brahe was an enthusiast but not really a scientist, so he did not know what to do with that data. So he came up to Kepler. He hired Kepler, who was a research assistant at that time. So he gave Kepler his charts to analyze, and that is how Kepler, after years of analyzing that, years of data, came up with this three famous Kepler's laws. So next we will talk about this. So next, that is the topic of the discussion next. Kepler's laws. So there are three laws that Kepler gave by analyzing the sky charts. Okay, and turns out these three laws became the main premise of the entire equation that Newton proposed and gave. Okay, so very important contribution by Kepler. Again, after study of years of data of charts of planetary positions, Kepler came out with three precise laws. So that is a wonderful thing. Again, Tycho Brahe's charts were so precise that whatever Kepler concluded was absolutely correct, and that is why Newton got his right equation. Okay, so it took years of again research and analysis by from these two guys, and then so here were the three laws. So before Kepler, people even after Galileo, they said they believe that sun is at the center of the solar system, and all the planets are moving around the sun in circular orbits. So before Kepler, people believed that. So let's just write that before Kepler, people thought that planets move around the sun in circular orbits. Okay. Now, please note one thing that all of Kepler's laws were purely based on analysis of night charts. So it was all observational. There was absolutely no logic to it. At least Kepler did not know the logic to it. Okay, so he just analyzed the chart, studies the night chart, and proposed these laws based on his observations. Now, Kepler did not know the logic of any of these. Now, the first law that Kepler gave is called law of orbits. Now, this law suggests that all planets move around the sun in elliptical orbits. Okay, with sun being present on one of the focal points. So that was a very interesting new revelation. In fact, now again, we guys can't show you because you are not equipped with enough mathematical skills. But in your higher classes, you can see that now if you try and analyze a two-body problem with the inverse square law, force governing their motion, you in fact get the equation of ellipse. Now you can actually derive the equation of an ellipse. Now with the, so when in college you realize, study a little bit more of advanced mathematics, you will realize that you can now prove it. You can now derive the equation of the ellipse, which you won't be doing right now, don't worry. So you know what an ellipse is. Every ellipse is characterized by two focal points, a semi-major axis and a a minor axis and a major axis. This is what an ellipse looks like, right? It has two focal points. So one might be here, F1, two focuses, right? Two foci it has. and F2, right? Then there is a major axis. So let's say this is the major axis, is usually represented by 2A. Then this is the semi-minor axis, which is B. Okay, so this is what an ellipse looks like. So what Kepler suggested was that all the orbits are in fact elliptical in shape, and the sun is always present on one of the focal points. Okay, so that's a very interesting thing. In fact, if you go to a maths teacher, they will tell you a lot of interesting properties about ellipses, right? So maybe in sometime you will try to prove this also. All right. So now again, when I say the sun has to be present on one of the focal points, so it's not necessary if you know. So there are two kinds of focal points, one on the left, one on the right. So it's not necessary that for every planet is the left focal point or the right focal point only. So let's try and see how the orbits could have been. So maybe one orbit is like this. Let's say here is an ellipse which is like this. Okay, so one planet is moving like this, and this would have had two focal points, right? Here, let's say this is the one focal point, and let's say sun is present here. Imagine sun is present here, and the planet is moving in such an elliptical orbit. For any other planet now, for another planet, you may have had even an ellipse like this. Okay, maybe like this. It should have had again two focal points, and the sun would have lied on another focal point now. So that is what Kepler suggested, that all the orbits are elliptical in nature. Okay, not necessarily having the same axes. So the ellipse may have had different axes also. So let's say if you could have had another ellipse like this. Again, sun is present on one focal point. Then you could have had another ellipse like this. Sun being present on another focal point. These are the kind of orbits that the planets will have around the sun. Okay, but sun for any ellipse will lie at least on one of the focal points. Okay. Now here it is worth mentioning one more thing. One more thing I want to tell you, that it's not the sun exactly about which the planets revolve. Okay, so a lot of we guys believe that planets are revolving around the sun. No, that's not the case. That model has a problem. Problem is that if imagine the sun was stationary, if imagine the sun was stationary, and let's say Earth was revolving around this, so you will have an issue there. The issue would be conservation of momentum. So let's say that this is the orbit of Earth. Okay, now imagine if the sun was stationary and the Earth was, let's say, here in its orbit and moving like this with some velocity v1, and then it came here with some velocity v2. Now you will realize that one due to angular momentum conservation, v2 would be greater, okay, than v1. Okay, we will talk about that, because the only force that the planet feels due to the sun is the force of gravity. So since that force of gravity is always directed towards the sun, definitely. So the angular momentum conservation tells you that V2 is greater than V1. We will talk about that later. Okay, so I have an issue that if I talk about the sun plus earth system, then the momentum is changing not only in magnitude but also in direction. Okay. Turns out actually both of them move about a common center of mass. So if there is a common center of mass here, then both the objects actually move around this. Okay. So imagine this is the orbit, here is the sun, here is the earth. Now the actual motion is happening about the common center of mass. The common center of mass remains stationary, and both the sun and the earth would rotate about this. That will make sure that the momentum of the system is always zero, because center of mass is always at rest. Okay. Now you will also realize that sun is so massive that actually the CM of the sun plus earth system lies inside the surface of the sun. Okay, so imagine what happens is that sun is so massive. So imagine here is sun, here is sun, and imagine here is earth. Okay, so the center of mass of this system, interestingly, turns out lies slightly inside the surface of the sun. That is where the CM of the system lies. Okay, that is why we don't notice this. We don't notice that both that the Earth and the Sun both are revolving around the common CM. Okay, but that is actually what happens. Okay, we will talk about that maybe in a bit later. But it's just worth mentioning here. Though this was not told by Kepler, by the way, this was not told by Kepler. This is something that I'm telling you extra. Kepler just talked about the elliptical orbits, but I still wanted to tell you here that the Sun and the Earth both revolve around a common center of mass. Okay. Now let's move on to the next law given by Kepler. So again, this was a purely observational law. Kepler did not know the logic of this. Kepler called this law the law of areas, and he said this law suggests that the line joining the sun and the planet sweeps equal areas in equal time intervals. Okay. Now, today we know that it is a consequence of conservation of angular momentum. Okay. So that is what we know today. So what that means is that if you see, let's try and understand that. So imagine you see a planet here, and then after some time delta t, the planet reaches here. So delta t time later, the planet reaches here. So the line joining the sun and the planet has swept this area, correct? We are calling this area 1. And imagine at some random instant later in its orbit, the planet was noticed to be here. Again, after delta t time, after the same delta t time, the planet moves here. Now, in this delta t time, the area swept by the line joining the sun and the planet is this. Now, this law suggests that these two areas will always be equal. So that's a very interesting thing, that always the line joining the sun and the planet would sweep equal areas. So what that implies is, imagine what that implies is that if you consider it moving from here, and in some delta t time it moves to here, and imagine the planet starts from here, and in some delta t time it moves here. So you realize for this area to be equal to this area, you realize if I roughly think of them as triangles, so the height of this triangle is higher, so the base of this triangle has to be lower. So you realize this distance S2 and this distance S1, if you compare, so in the same time delta t, you will realize S1 should be much greater than S2 in order to ensure equal area. Devra Varun says, "Hi sir, your video has a little bit of lag." Okay. So yeah, the net fluctuates a bit. Okay, but I hope the lag is not too much. I hope you're able to understand these things in any case. If there is a problem with that, then let me know. Maybe I can try restarting my software. But the net does fluctuate a bit, so there may be slight lags here and there. But overall, if there is a problem in your understanding, then you can let me know. I will try restarting my video and let's see. Okay. Now, as I was saying, so the planet turns out will move faster when it is closer to the sun, and it will move slower when it is farther away. Okay. It turns out that happens. So that's a very interesting result of Kepler's second law. Okay, that a planet, when it is closer to the sun, moves faster, and when it is farther from the sun, it moves slower. So let's see if we can prove that. So now we will attempt to prove that this is something that we can prove. This is something that we know. The logic also, we know the maths also. So this is something that we can easily prove. So as a matter of proof, what I will do is that imagine if the planet is somewhere here. Okay, so imagine that during its motion, the planet was here and currently moving with a velocity delta v, some v. You know the velocity would be tangential to the trajectory always, right? Imagine it is moving like this. Now in small time dt, let's assume that it moves to here. Okay, so this is its motion in small time dt. So the distance moved would be v dt. Okay, the distance would be moved will be dt. If I assume that right now the distance from the sun is some small r, and for the small time duration of dt, I can assume that this distance almost doesn't change. So this also can be assumed to be r only. Only a little bit, sir. It's okay. We can understand what you're explaining. Oh, that's good. That's good. Yeah, because I've seen a lot of times that the net just keeps on fluctuating a bit. So there is nothing much I can do. If there is a major lag, then you can tell me. Then I can try restarting my software and changing my settings or something. But yeah, this unfortunately seems to be a problem consistently happening. So if the angle turned by this line joining the sun and the planet is making some angle d theta. So imagine this line turns by a very small angle d theta. Then what is the area that it should? So you realize this is part of a small circle. So imagine this planet was moving in a radius of circle r. So if it had moved for a complete angle of 2 pi, it would have covered an area of pi r square. Okay, so what is the area that it would have covered if it moved only by an angle d theta? Let's try and find that. So I can say, so if theta equals 2 pi, area covered would have been pi r square, right? So for 1, if theta equals 1, so I can also say if theta equals d theta, if the angle covered is d theta, the area covered would be pi r square into d theta over 2 pi. Okay, I'm just applying unitary method. Okay, nothing much. Just applying unitary method. I'm saying if it turned only by an angle of d theta, then the area covered would have been this. Okay, so turns out this is what I'm getting. Now this d theta is the angle. Angle can be written as the arc length over the radius. Okay, so I can also say dA, the small area of that swept would be equal to r square by 2 into d theta, which can be written as v dt, the arc length over the radius. Okay, so from here what I get is dA over dt. dA over dt is r over 2. Now if I multiply the mass of the planet divided by the mass of the planet, now numerator tells me the angular momentum of the planet with respect to sun over 2 times mass of the planet. This is a very important formula. This is a very important formula. You need to memorize this. A lot of questions are asked from this. Okay. So dA by dt is also called the aerial velocity. It is the area swept per unit time. You realize that numerically it is coming out to be the angular momentum of the planet about the sun over 2 times the mass of the planet. Now you will realize one more thing. One more thing you will realize that wherever the planet goes, the only force acting on it the only force acting on it is the force of gravity, gravitational force of the sun, right? So you will realize that force experienced is like this. This is the force of sun. Now here also it is the force like this. It is the force like this. So wherever the planet is, the force is always directed towards the sun. So can I say that this force of sun's gravitational force cannot produce any torque about the sun itself? Now, please note that the orbit and the size of the orbit are so huge that for our analysis, I can treat the sun and the planet roughly as point objects. Okay, so if I'm roughly treating them as point objects, then I can say since the force of the gravitational force acting on the planet passes through the sun, that is the property of gravitational force, which we will realize later. So the torque produced by this force about with respect to sun is zero. Okay, so I can say since the force of sun's gravitational pull is always directed to the sun. Therefore, it cannot produce any torque about with respect to the sun. Correct. Now you should also realize that if on any moving object, the torque about a point is zero, then its angular momentum is constant. We just finished the rigid body motion where I had told you. Also, if torque on planet with respect to sun is zero, so L of planet with respect to sun is constant. So that here the aerial velocity, so the area swept per unit time, will be constant. Okay. Why? Because you see the numerator has angular momentum of the planet with respect to sun, so that is constant. Mass of the planet, of course, is constant. So Shivam says, "Sir, plus pay next course kab banaoge waiting." So yes. I've been a little busy. Haven't been getting much time to plan that. I have had it planned actually. So I'll just need to uh, launch it. Okay. So maybe give me a couple of days. Within a couple of days, I will launch my course. It will start either by this weekend or from Monday. Okay, Shivam. All right. So I hope you followed the entire discussion. So again, this thing was not given by Kepler. Let me remind you again. Kepler only said this. Kepler's law only said this, that the line joining the sun and the planet sweeps equal areas in equal time intervals. That's it. That's it. The rest, we are proving by with the help of our knowledge from Newton's laws. So you realize Kepler came before Newton, by the way. So until Kepler's time, there was no idea of momentum. Forget about angular momentum. There was no idea about the gravitational force. So there was no idea of forces and why this motion is happening, by the way, at the time of Kepler. So the proof that we are giving was not given by Kepler. We are, with our knowledge of Newton's laws, know that proof. Now, of course, Newton could understand this. That is why he was able to derive the expression of the force. Okay, so yes, Shivam, तब तक rotation के बहुत सारे problems करो यार. अभी I just finished rotation there also, right? So I'll be holding a lot of special classes for problem discussion on rotation. So you keep attending those and keep practicing rotation. So I'll give you 1 week's time for your practice of rotation problems. And on the coming Sunday, I think you are supposed to have a quiz on rotation, right? So तब तक उस पे focus करो. Practice rotation. Ask me your doubts and let's see. Okay. All right. Now moving on to the third law that Kepler gave. The third law that Kepler gave is called law of periods. Now, this law suggests that if t is the time period of revolution of a planet around the sun and a is the semi-major axis of the orbit, then t square is directly proportional to a cube. Please remember that. Or in other words, I can say t square over a cube equals constant. So he realized that for all the planets that he could see, this ratio was coming out to be constant. By the way, I don't know if you, Sarji, willing be solving every manipulation you told in class. Great. Okay. So that should give you some confidence then. All right. Now please note, at the time of Kepler, there was only 5 planets known other than Earth. So they only knew about I think Mercury, Venus, Mars, Jupiter, and Saturn. That's it. That's it. So for all these, see, there were years of data. So the time periods of all the planets were known. The semi-major axes of all the planets were known. Kepler realized that somehow the ratio of t square is to a cube is coming out to be constant. So that's again the law given by Kepler. Again, no logic of this was known. Now, please note that sometimes what you will find in a few books is that they will prove this thing using Newton's laws, okay, which is slightly wrong. Okay, why? Because Newton actually derived his expression using these results. Okay, so should I learn rotational motion before going ahead with gravitation? So not really. If you know the basics of circular motion, then that should be enough. If you know the basic ideas of centripetal force and centripetal acceleration, then that is enough. Rotation, you just need for one Kepler's law, the angular momentum. I hope you know MVR, that is the angular momentum of any point object, right? So if that is known, then that should help you. Okay. And of course, it is always better to study that topic. In any case, it is One of the most important topics of your entire syllabus of class 11th and 12th. Okay. So again, as I said, sometimes you will see books proving this fact using Newton's laws, but that's actually wrong. Reason for that is Newton derived his expression based on this law. Okay. So if Newton based this law to obtain his expression, of course, his expression will prove this back. So that is not how it happened, though. Okay. The Kepler was someone's student, or he had been other student. Yes, yes. So Kepler was a research assistant hired by Tycho Brahe. Okay, he was a research assistant. Tycho Brahe was the main guy who prepared all the charts. So Kepler was his assistant who analyzed these charts and gave the laws. But now everybody just knows Kepler's name. Nobody knows Tycho Brahe's name. Okay, yeah, that is slightly that. Okay, now let's try some problems. Okay, so here you've been told a planet of mass m revolves around the sun in along an ellipse, which so that its minimum distance from the sun is equal to small r and maximum distance is capital R. Find its time period of revolution around the sun if the average distance of Earth from the sun is d. So try this. So let's see if you can find that. Now Earth's orbit turns out it's almost a circle. So the eccentricity, every ellipse has a eccentricity associated to it, right? So it turns out the eccentricity of Earth's orbit is very close to 1. You know, uh, you can treat a circle as a special case of ellipse, right? Where the semi-major axis and the semi-minor axis become equal. So turns out, which will have eccentricity 1, E equals 1, right? So turns out for Earth's orbit, E is actually almost very close to 1. Okay. Now you will realize I told you earlier that the sun and the planet both move around the common CM. So the common CM, you realize because the Earth is not so massive, lies almost inside the sun. For Jupiter, it would be very off. The slightly more off from the sun's center. That is why you will see the eccentricity of that is highest. Yes. Okay. Sure, Shivam. Bye bye. Take care. Okay. Now, so how about this? How would you go for this? Okay. Let's see. Let's see. So you've been told. Let's imagine that here is your sun. Here is your sun, and here is your planet. Imagine moving in a circle orbit. So you must realize that the closest distance is given to you small r, and the largest distance is given to you as capital R, right? So can you say this semi-major axis of this orbit would be small r plus capital R? Okay. So I can say for the given planet, 2a equals small r plus capital R. So a is nothing but small r plus capital R by 2. Now for Earth, for Earth, we know that a dash, let's call that the semi-major axis of Earth, is almost equal to d because Earth almost has moves in a circle. Okay, semi-major axis would be roughly equal to semi-minor axis would be roughly equal to d only. Okay, so from here I can say that from Kepler's laws, I know that p square over a cube equals constant. So p1 square over a1 cube would be equal to 2 square over a2 cube. So from here I can say time period of the planet would be equal to time period of Earth to r plus r over 2d whole cube. Time period of Earth we already know 1 year, so we can estimate the time period of the planet would be r plus r over 2d to the power of 3 by 2 years. If I could tell you the exact values, you would have actually able to figure out the exact time period. Okay, that's a very interesting again use of Kepler's law. Now, with the help of Kepler's law, if you knew the minimum and the maximum distance of any planet with respect to the sun, you could have predicted its time period. Okay, all right. So here is another problem. So again, this is related to the second law. Okay, so this one says that the ratio of Earth's angular momentum about the sun to its mass is a 4.4 into 10 to the power 15 meters square second per second, and the area enclosed by Earth's orbit would approximately be. So that is what you have to find. So give it a try and let's see if we can solve this. So this is a good example of a problem related to the second law. So let's try and solve this. Let's see if you can get this correct. Okay, Pandey is fine. All right, how about others? AP says it's D. Yes. Okay. How about other people? How about other people? Let's see some other answers also. So AP generally keeps giving all the correct answers. So yes, let's wait for some others also. Okay, let's see some what others have to say. Okay, so S Pandey also says D. Okay. So I think Tanya was also trying. So let's wait for Tanya's answer as well, and then we will look at the solution. Yeah. All right. Hmm. Okay. Let's see. Okay. So Tanya also says D. All right. So let's see how you would have solved this. I think D is the correct answer. So you guys are all correct. Very nicely done, people. Let's see how. So if you realized when we studied the second law, you should have noticed that dA by dt, which is also known as the aerial velocity, is equal to angular momentum of planet with respect to sun over 2 times mass of the planet. Correct? Now in this question, you've been told that the ratio of Earth's angular momentum to Earth's mass is this. So the aerial velocity of Earth would have been 1 by 2 times 4.4 to 10 to the power of 15. That is 2.2 to 10 to the power of 15. That's the aerial velocity. Now, what is the time in which the Earth completes the entire orbit once? Okay, so time I know. Now, delta t is 1 year for the Earth to complete one revolution, right? 1 year can be written as 24 into 365, 2600 seconds, right? This was meter square per second. So, to find the area of Earth's orbit, therefore, area of Earth's orbit would be just the aerial velocity k by dt times delta. It would be 2.2 into 10 to the power of 15 into into this time in 224 in 5 236. Okay. So yes, that is how you would have found the answer, and the answer comes out to be D. So you realize that is how huge the area of Earth's orbit is. So even this is in meter square. Even if you find it in kilometer square, so 10 to the power minus 6 can be multiplied to this. So it would still have been 7 into 10 to the power of 16 kilometers square. So huge orbit of Earth. Okay, so yes, that is the correct answer. Well done, people. Okay, now let's consider another very interesting problem. A very interesting problem would be if if the Earth suddenly stops revolving around the sun, then how much time will be taken by the Earth to fall into the sun due to its gravitational force? Again, a very interesting, tricky problem. However, let's see if you can figure this out. Okay. So how much time will Earth take into falling into the sun? now you realize now you realize, even if you knew the Newton's law equation, and even if you knew the distances, then also finding the time is a huge ask. Now you can, however, very easily answer this using Kepler's laws. In Kepler's laws, I can easily answer this. Okay, so any idea how you would have gone about this? Okay, what we can do is let this as your challenge problem. So try and figure out challenge problem for homework. Okay, this is a very tricky problem, but hint, of course, I'm discussing it under Kepler's laws. So you could have answered this using Kepler's law. Okay, very good problem. So think about this, and we will discuss this maybe in the next class. Okay. All right, moving ahead, let's talk about Sir Isaac Newton's law of gravitation. Okay. So again, this is one of the very few laws in physics which are called the universal law. So you will realize there was another law that you will study later in heat. So that is a universal law of radiation, or Stephen's law. That is also one universal law. Apart from that, this is the only I think law that we call universal law. So why do we call it a universal law? Because turns out the law of Newton holds exactly true, or follows obeys the same equation for small little particles like two protons, two electrons, one proton and electron. And exactly the same equation would be valid even for celestial objects like the force between the planets and the Earth, Earth, and the sun and the moon. So that's a wonderful thing by given by Newton. Now it may not appear to be a big deal to you guys right now, but imagine Newton gave these laws in the 17th century. Back in 17th century, when people were getting imprisoned, just after only a few years after, when people were getting imprisoned by because of saying something logical, and they were even getting poisoned because they could prove it. Okay, at that time, Newton to give a law, and which he claimed was a universal law. So earlier that time, what happened was that people used to believe that laws of laws governing everything happening on Earth are different, and all the laws governing the motion of all celestial objects are different. So they had this idea of Earth and heaven. So they said the rules of heaven are different. So the rules governing the motion of celestial objects are different, and the rules governing all the motions happening on Earth are different. It was Newton who said no. These are laws of nature, and laws of nature are laws of nature. They are universal. There are no two kinds of laws, no matter what. So that was a huge achievement. In fact, Newton's law of gravitation can be considered as one of the biggest generalizations mankind has ever seen. Okay, so imagine what he did was that he was, as you know about the famous apple falling story, right? So Newton, after Kepler suggested that all planets are moving around the sun in elliptical orbits, so all the scientists were trying to see. We knew this, that planets are moving around the sun in circles. Now, why that was still not known, and how do you mathematically describe that? So, a lot of scientists were going for it. They were trying to develop a mathematical model which could have described this. So, while thinking about that, Newton was thinking about the motion of moon around the sun also, around the earth also. Now, Newton had already given laws of motion. He had already developed laws of motion. So, he knew that whenever something is moving in a circle, it has an acceleration. Now, what causes an acceleration? An acceleration is always caused by a force. So, there has to be a force acting between the earth and the moon. Okay. Now, while sitting under the apple tree, when the apple fell on him, he realized that again, if the apple got ripe, so why did it fall down? Again, it was at rest. It had inertia. It should have stayed at rest until unless a force was applied. So then he realized, yes, Earth must have applied a force. That is why the apple fell. So what Newton suddenly is, what struck him was that Earth seems to be applying a force on Moon, and Earth also seems to be applying a force on the apple. And now Newton, being Newton, had the third law also, Newton's third law. So he realized that since this Earth is moving around the sun also, so sun must be applying some force on Earth, and from the third law, Earth must be applying an equal and opposite force on the sun. So he realized that Earth seems to be applying a force, attractive force that is on the sun, attractive force on the moon, attractive force on the apple. So that is what led him to make this generalization where he goes on to say that every mass in the universe, that is a huge statement to make, that every mass in the universe will exhibit this property. Not only small objects like small masses, something like Earth and Moon, also something like Earth and Apple, also any two masses, you go anywhere, any two masses in the entire universe will exhibit this property. So every mass in universe attracts every other mass with a force which is directly proportional to the product of the two masses and inversely proportional to the square of the distances between them. So again, when I said that Newton's law is considered to be one of the biggest generalizations ever made by mankind, so that is what I mean. For somebody to go on and say that this is something that will be true for everywhere in the entire universe was a very bold assumption and a very bold, you know, leap of faith in nature. Okay, so that has been the characteristic of all the scientists. All the scientists have possessed a great amount of faith in nature. They have always believed that the nature is consistent. Okay, so if I've seen Earth attracting sun, the moon, the apple, then Earth must be attracting everything. And similarly, by third law, the sun is attracting the Earth, the moon is attracting the Earth. So similarly, everything must be attracting the Earth back also, right? So that is what the generalization. That is where it comes from. He says that every mass in this universe does that. Now, mathematically, this law is expressed as F equals G m1 m2 over r square. So as I said, that the force was proportional to the product of the two masses and inversely proportional to the square of the distances between them. And then that also can be logically derived with the help of Kepler's laws. So this equation actually, this equation can be derived with the help of Kepler's laws. So it was Kepler's laws that Newton used in a derivation of this. Some observations were involved, and then use of Kepler's law was involved, which made him give this equation. Now, interestingly enough, Newton did not know the value of G. G here is called the universal gravitational constant. So this law just says that F is directly proportional to m1 and m2 and inversely proportional to the square of the distance. From here, we say that F equals some G m1 m2 over r square, where G is called the universal gravitational constant. So it is a constant of proportionality. Okay, universal gravitational constant. Okay. Now, please note that the value of G was not known to Newton. Newton simply suggested that this kind of equation, if I consider, then it explains everything. All our observations can be explained with this kind of an expression. So Newton suggested this equation, but it was incomplete. He did not know the value of G. In fact, the value of G was found much, much later by a famous guy named Cavendish. We will talk about his experiment and how he found the value of capital G. So today we know that the value of capital G is 6.67 into 10 to the power minus 11. Now in 1700s, I think that was when Cavendish was able to find the value. He gave a pretty accurate value. The value that he predicted was 6 into 10 to the power minus 11, which was an amazing observation considering the time at which it was made. Okay. Now please note one very important thing, that this law is only defined. So that is again very important. So again, as I said, there is a confusion that a lot of students have. Okay. So a lot of students don't know this, that this law is only valid for point masses. So when I ask students, this happens to class 12 students, 12 pass students in 12 pass batches. They have no idea. When I ask them, two objects like this and like this are kept close to each other. So this has mass m1, this is mass m2. What will be the force between them? And when I ask them what is this R, so there can be a lot of confusion, right? So R can be this. This is this R is center to center, or rather center of mass to center of mass distance R, or is it the end to end distance which is R? So what is R? So trust me, a lot of people tell me that this is the R, distance from center of mass to center of mass, which is wrong, which is absolutely wrong. I will prove that it is wrong. So if you believe that R is the distance from center of mass to center of mass, then you were thinking about it the wrong way, and correct that immediately. The point is that Newton's law of gravitation is valid only for point masses. So it cannot be applied for these objects. You cannot apply Newton's law for these objects. It would be wrong. You cannot write F equals G m1 m2 over R square equation for this. No. You could have written it for 2 point masses having masses of m2, and there would have been no confusion about R. Okay. There the R would have been this. Simply this. Okay. So again, this is wrong. This equation is slightly wrong, because this gives you an idea that maybe you can apply it for the bigger masses. That does not happen. Okay. Anyhow, so it is only valid for point masses, and this kind of figure is also wrong. That is wrong to draw such a figure. Okay, that is what I wanted to tell you here. So that's it, guys. Our time for today is up. So this is where I would like to wrap up today's, and we will talk about uh, the Newton's law in detail in the next class. So fortunately, today this is the only time that we have. So let me wrap up today's session here. And before I leave you, let me tell you about the Unacademy Plus. If you haven't got this subscription, what are you waiting for? There's absolutely no time to waste. So IDJ is such a competitive exam. You will, as I keep telling you, you will need all the help that you can get. This is one great way of getting help. Get yourself the Unacademy subscription and jump ahead in the competition. Okay, and how do you get this? So you need to install the app, then go to the plus section of the app, select your goal as ITJ, click on the get subscription button. Now, once you do that, you'll be redirected to the payment page, where do not forget to use the code RD Live to get a 10% off, and then click on proceed to pay. Okay. Now you can select from the plus and the iconic subscriptions. So talking about the iconic subscription is a new feature that Unacademy is offering to all the students who are looking for more personal attention. Okay. This kind of subscription will take your ITJ preparation to the next level, as you will be assigned personal coaches, where you'll be part of a lot of ITJ workshops. You will receive timely expert guidelines. You will have a study planner. You will have text analysis sessions. Okay, and now you can even win yourself these subscriptions by taking part in the Unacademy Combat, which is going to be happening live next on the 20th of December. You can enroll now using code RDLive, compete, win some cool prizes. Okay. If you like today's video, then don't forget to press that like button and start sharing more people, because I don't think you guys share these videos enough. So don't be selfish. Let as many students get benefit of this quality free educational content as possible. The idea is to make this free quality education reach as many students as possible. So share it with your friends, share it with everybody you know, and everybody you know thinks could use this. Okay. Now, if you're new to the channel, don't forget to subscribe and don't forget to press the bell icon. Okay. And the PDF of all the notes, of all the slides used in today's lecture would be available for download very, very soon. Yeah, those of you who are following us on the JEE English channel, if you haven't connected with us on the Telegram app, do it right now so that you keep receiving all the timely notifications of all the lectures and amazing sessions happening here. Okay. Next, one more quick announcement. So tonight we have a special session. Okay, special session tonight where I'll be talking about special session at 8:30 tonight, where I'll be talking about how to attempt your papers, how to attempt competitive paper. We will mainly be focusing on JEE papers, but these tips would also be useful if you are looking to take the NEET and other competitive exams, which involve MCQs. Okay, so that is what. So how to attempt a competitive exam paper. So this is the session that we are going to be having at 8:30 tonight. Don't forget to join me for that. That will be very, very useful for you, all you guys who are looking to prepare for your JEE right now or even in the future. Okay. All right. So with that, I will conclude today's class. And before I leave you, let me remind you, RD Live is my code. So if you're planning to get yourself the Unacademy subscription, you can do that using this code and enjoy a cool 10% off on all your. All right. So I'll see you then at 8:30. Don't forget to join me back in 3 hours. Okay. And we will talk about some really, really useful points which will help you increase your marks. Okay. And make sure that you deliver what you've learned properly. Okay. So till then, you guys take care and keep studying hard, keep practicing.